To this week's Crown Seminar. Our first speaker is Shenglin Huang from University of Pennsylvania. Shenglin is a fifth-year PhD student at the Department of Mechanical Engineering and Applied Mechanics, and his PhD research focuses on data-driven model discovery of non-equilibrium phenomena by combining tools from continuum mechanics, statistical physics, and machine learning. Before joining University of Pennsylvania, Shenglin obtained his bachelor and master degrees from Peking University. He will be talking about his recent research on model discovery for non-equilibrium processes via stochastic thermomechanics. Welcome, Shenglin, and you may want to start your presentation.
Yeah, thank you. Thank you, Zhongren, for introduction. Hi, everyone. I'm Shenglin Huang. I'm a fifth-year PhD student in University of Pennsylvania, working with Professor Celia Reyna. Today, I want to talk about some of my recent work, and the title is Data-Driven Model Discovery for Non-equilibrium Processes via Stochastic Thermomechanics. And this is actually the title for my PhD thesis. So our group mainly focus on non-equilibrium processes. We study the non-equilibrium phenomenon and do coarse graining to multi-scale modeling from the microscopic to the continuum level. Particularly, we usually use data-driven strategy, want to use the big data in both microscopic and continuum level to discover the continuum modeling. So non-equilibrium phenomena are ubiquitous in nature. We can find different behavior in different systems, such as the diffusion in liquids, the viscoelasticity and plasticity and fracture in solids. And we can also find the solid-like friction together with liquid-like flow in the granular media. And we can also find this flow behavior and elastic response for living systems. And non-equilibrium phenomena are also evolved in the state-of-art technologies, such as soft materials, additive manufacturing, nanotechnology, and biomedical applications. As we can see, these phenomena are so different from system to system. So understanding and modeling this behavior for different systems is actually a very hard problem in both theoretically and computationally. So theoretically, we have well established the equilibrium thermodynamics and statistical mechanics for 100 years. However, for the non-equilibrium process, everything is different. The only well-accepted law is the second law of thermodynamics, which states that for closed system, the entropy will never decrease. However, the second law only tells us an inequality. It is not an equality, which means we only know which direction does the system evolve, but you don't know how does the system evolve. So in order to construct the equality to describe the non-equilibrium evolution, people have discovered plenty of different theories. However, none of them are universal or well accepted by all the people. And some of them may still contradict with each other. So computationally, we can definitely do molecular dynamics to see how does the system evolve in non-equilibrium processes. However, MD simulation is largely limited by the time scale and the length scale. It is nearly impossible for us to simulate a real system for MD in real space and time scales. Therefore, when doing multi-scale modeling, in order to save computational efficiency, people usually need to assume many phenomenological assumptions. However, does this assumption truly agree with the physics in a smaller scale? That's what we need to think about. So in today's talk, and also for my PhD research, I focus on the development of new theoretical and computational paradigms to understand, predict, and design far from equilibrium material behaviors, particularly use data-driven method. And I will combine the tools from continuum mechanics, statistical physics, applied math, and machine learning to tackle with the non-equilibrium mechanics. So today I will basically introduce two of my recent works The first one is called variational Onsager neural network. It's a machine learning strategy to learn non-equilibrium PDEs. The second one, although it's not machine learning, but it's still data-driven, it is the statistical mechanics framework to extrapolate non-equilibrium material behaviors and with uncertainty quantification. So let's go to the first work, the variational Onsager neural network, or called VONS, a thermodynamics-based variational learning strategy for non-equilibrium PDEs. So there are many systems can be described by variational principles. For example, in elasticity, we have the minimum potential energy. That we have the potential energy for the system, and when you do a variational derivative for the potential energy, you can find the equilibrium state of the system. And for the classical mechanics, we have the Hamiltonian structure and the Lagrangian Euler equation. So similarly, for the non-equilibrium processes, we have also have a variational structure that calls the Onsager variational principle. So if the system is isothermal without inertia, we can define a variational, a functional called Rayleighan. So this Rayleighan is a functional of the Z and W. Z is called the state variables. It is like the displacement of the system, or the strain, or the concentration of the diffusive system. So it is like a snapshot for the system. And the process means the rate or the change between each snapshot, such as the velocity field, the strain rate, or the flux. So this Rayleighan is defined as the summation of the free energy rate plus dissipation potential and plus the power of external force. So here I want to emphasize dissipation potential describe a potential for the irreversible phenomena. So in analog, free energy is the potential for the reversible phenomena. So Onsager variational principle says, if we do minimization for the Rayleighan with respect to the process variable, only process variable W, we will find out a governing equation that states the evolution of these non-equilibrium processes. And moreover, if we want to count inertia effect, we can also simply add the effect from the kinetic energy K. So why we choose Onsager variational principle? So first, it is an extension of the Onsager reciprocity relation. So Onsager reciprocity relation describes the linear response for the near equilibrium phenomenon. And Onsager variational principle can be viewed as the extension for the far from equilibrium phenomenon. And moreover, recent years, mathematician has shows that it has a strong relation between the microscopic stochastic process and the continuum level non-equilibrium process. By using the large deviation theory, we can connect these two processes with the Onsager variational principle. So moreover, when describing the non-equilibrium process, we also need to have some constraints, particularly the second law. So the second law of thermodynamics requires that we have three constraints for the system. The first one is the dissipation potential should be a convex function on the process W. Second is when process is zero, the dissipation potential is zero. This is like a collaboration of the 0 point. The third one is the derivative of the dissipation potential with respect to W, which means the dissipative force. So the dissipative force should be zero when W is zero, which means that if there is no process, there should be no dissipation, which makes sense. And moreover, since we want to do continuum modeling, so we'll assume these local assumptions, that is the free energy and the dissipative potential, the dissipation potential can be described by the local density and doing a volume integral. So to give more example to show how does this Onsager variational principle works. First, for solid mechanics problem, we can use the deformation gradient F and the internal variables Q to describe the system states, and use velocity field and the internal variable, the time rate of the internal variable as the process. We can find out the following governing equation by doing this variational principle. So the first equation is actually the balance law or the evolution of the system. The second one is the traction boundary condition. And third one is the evolution for the internal variable. So also we can use Onsager variational principle to describe the diffusion system. For example, if we use the concentration as the state and flux as the process, and if the system satisfies mass conservation, we'll find out the following governing equation for the system. So as we can see, if we have a system, we know the free energy and dissipation potential of the system. With the Onsager variational principle, we derive the equation with respect to these potentials. And with this known potential, we can solve the governing equations to know how does the system evolve. However, here I want to focus on an inverse process. So if we have a new system or unknown system, for example, we do experiment of this system, or we do molecular dynamics simulation for a system and know some evolution, we obtain some trajectories. So can we infer what is the free energy and dissipation potential of the system to characterize this non-equilibrium behavior? So in order to do so, I use machine learning strategy. So we propose this variational learning structure to learn the non-equilibrium PDEs. So we take the state and process variables as input, and here we will use two different neural networks to learn the two thermodynamic potentials, the free energy and dissipation potentials. And then by using the physics-informed neural network strategy, we construct the loss function based on the governing equations we obtained from the variational principles. And then we do minimization over this loss function, and so that we can find the optimal state of the system to obtain the two potentials for the system. So moreover, in this process, I also use some other techniques. One is called integrable neural networks. This is because from the variational principles, the equation we obtain, in the equations, the free energy and dissipation potentials themselves does not directly appear in the equation. Instead, they only appear as their derivatives. It's like we can only find the, for example, the traction or stress or chemical potential. They're all the derivative of free energy. We can only have this derivative in the functions. We cannot, in the equations, we cannot find themselves. So in order to learn this function, we want to the learned function to have some integrable properties. This, next is the fully or partially input convex neural network. This is because when we apply the second law of thermodynamics, we want the dissipation potential to be convex on W. Finally is a called adaptive loss weights developed by Professor Ponticaris. So this one is used to tune the loss weight automatically, and it can largely increase the robustness of the training process. So go to the detail of the structure. First is the structure to learn the free energy density. So this integrable neural network is basically just a feed-forward structure. So the only difference between the fully connected feed-forward and the integrable neural network is that here we want the activation function G and its derivative G prime to be activation functions. So that we'll use the soft class activation functions because its derivative is the sigmoid. And moreover, we want to impose some constraint for the free energy. like to set a 0 point when z is 0. So to do so, we can just simply use this trick. Here, the f tilde is the direct output of the neural network, and we'll just subtract the 0 point, and this f will be the free energy we want to learn. So for learning dissipation potential, it's a little bit complicated. So first we consider a simpler case where the dissipation potential of psi is only a function of the process variable W, and it is convex on W. So here we use this fully input convex neural network. So this neural network is a feed-forward neural network plus plenty of pass-through layers between the input layers and each layers. So in order to make the output being a convex function, we need these red weights to be non-negative and set the activation functions to be convex and non-decreasing. So for more complicated cases or more general cases, free energy is, the dissipation potential is a function of both Z and W, but only being convex on W. So following is the neural net architecture to learn this convex function. So basically, this has two parts. The first, the upper part is a feed-forward, fully connected feed-forward neural net, and the lower part is the left-hand side structure, and they have plenty of complicated interaction between them. And also to make the psi being convex on W, we also need the red weights to be non-decreasing, non-negative, and the activation function to be convex and non-decreasing. So in order to satisfy this, soft plus is also a good function to choose because it's convex and non-decreasing. And also, as I mentioned before, the second law has three constraints. The first one is convexity, which is imposed in the neural net. For the other two, we can also use this trick to do so. So here, the psi tilde is the direct output of the neural network architecture. And by doing this mathematical trick, finally, this psi is the dissipation potential we want to learn that strongly satisfy the second law of thermodynamics. So in order to illustrate my neural net architecture, I'll use three examples to show it. The first one is a phase transformation process of the coiled-coil protein. So this protein is described by a non-convex or double well free energy profile. So when you pull this protein, it will jump from the first minimum to the second minimum and have a phase transformation process. So for this structure, if we want to learn the free energy and also dissipation potential from the evolution, I use Onsager variational principle to, here I assume the free energy is a function of local strain and dissipation potential is a function of local velocity. And using the variational principle, we can find out the following governing equation. Here is the data I use to train the neural network. This is the evolution of the displacement field. So here we can see there is a phase front to show this phase transformation process. And this is the pulling the external force, the traction boundary condition. So I use the two neural nets to learn the structure, to learn the two functions. And each neural net has two hidden layers with 25 neurons per layers and construct the loss function based on the equation we learned. So here is the result. This is the free energy and its derivative, and the dissipation potential and its derivative. And we can see all the results are pretty good. So here I want to emphasize is this neural net architecture can help us to recover the non-convex free energy from data, which is not a very trivial task for some traditional method. because non-convex free energy is usually hard to explore.
So, Shenglin,
Yes.
can I ask? So the way that you pose the problem here, the boundary conditions are known, right? We have the governing equations. So it's just like a straightforward problem, right?
What do you mean of straightforward problem?
It's a forward problem. In other words, you've solved for f and psi.
Yes.
Given initial conditions and given the equations.
No, we don't have initial conditions. So here is the data itself is just generated from.
Okay, so you don't have initial conditions.
I don't have initial conditions, so I only have some data we obtain from some experiment or simulation. So here,
right, that's what I'm trying to see. What data is that? These are data on the on what is U?
U is the displacement field of this protein. And from this displacement field, we can obtain the velocity field and the stress field, the strain field. And
so you have five snapshots of displacements, right?
Well, not just five. This is just some illustration.
Okay. So, well, you didn't tell us what you're solving then.
Okay, sorry. So I have this evolution of the system. So with these. So originally, the evolution itself is just a displacement field together with the traction we measured on the boundary. And from the displacement field, we can calculate the strain field and the velocity field. They are all functions of space and time. So we will use this data in space and time, but we don't really care their order as long as, so for each point, we have a given strain in that space and time point, and we'll just calculate this loss function using.
But you don't want to tell us how many snapshots, how many points, space time, how many points totally you use here?
I forgot the detail. Let me see. From this simulation, the spatial point is, if I remember correctly, is 25 spatial nodes, and snapshots. I think in total, space multiply time is several, maybe 30 or 300,000. I think it's 30,000 data points for both in the PDE and for boundary condition.
And you integrate for what? One nanosecond?
No, I don't do integration. So here you can see the loss function, we have PDE and boundary condition. And this is, for example, for this PDE, I only need the strain point for each space I and time t and packed with its neighbor to calculate the spatial derivative. And as long as this, so for each space and time point, we can calculate this. We don't really care about are all these data points related to each other? Are they?
I'm confused. If I look at your PD expression, you sum over J, but the index is I, and then I don't see any time.
Well, so yeah, J is a compact index for both I and N. So J is both I and N. I didn't show that clearly in this PPT. It's in the paper. So how should I say this? So for example, for us, space and time, let me draw some plots. So it's, for example, if this is space and if this is time, so in principle, we have plenty of snapshots for all these points for the evolution, but we don't really need all those evolution. For example, we can only use some points of this space and time, and no need to fulfill the full space. So this is one of the I and N. This is another I and N. And the J is just a compact, index for I and N. So we just picked some I and n in space and time, and to as long as they can somehow cover the input variable space, such as they can fulfill the string field space and velocity field space, and then we can use this data to calculate this loss function. So there is no integration during this process. We just directly calculate.
No integration, but the intervals in time. What is the interval in time?
So time interval is still that. So we already have, for example, if we get the evolution of the displacement field, we already have a space and time discretization, and we can calculate the stress and velocity field based on that space and time discretization.
No, that's not what I asked. I asked if you go back. Can you go back, please?
Yeah, wait a minute. Yeah.
Right. So your snapshots show like nanoseconds, fractions of nanoseconds, right? So
yeah.
So the interval goes what, from 0 times 0 to 1 nanosecond total, or 0.1, let's see, 0.5 nanoseconds? I understand the time scales you're dealing with, and what is this protein? Is this protein from a protein bank, or is it just an arbitrary thing?
This protein is the free energy profile is obtained from a literature, and we just directly use their free energy and some of their parameters we first to solve this equation and generate this data, and then we use this data to train the neural net to learn the profile again.
Okay.
Yeah. Does that answer your question?
So not exactly, but please go on.
Okay, sorry. Okay, so yes, we use the data in space and time for the string and velocity field here in space and time, and then we can calculate the loss function and to do this learning process and learn the free energy anticipation potential. So the next example is a reduced order modeling for a viscoelastic bar. So this is a three-dimensional viscoelastic bar and pulled in this one direction. So instead of when we want to recover the full three-dimensional response, we're here only interested in the one-dimensional response. So we here just assume the state variable as the one-dimensional string and viscous string, and the process W as the one-dimensional strain rate. So, and with the Onsager variational principle, we can obtain a one-dimensional governing equation. And here I want to emphasize, if we start from a three-dimensional equation, we can also when doing this reduced order modeling, we can obtain exactly the same one-dimensional the equations. But this reduced order modeling is usually not an easy task to do for more complicated structures. So here we still use our ones to learn both free energy and dissipation potentials. And here is the results, the learned free energy and its two derivative, and the dissipation potential and its derivative. So here the key point is that this Onsager variational principle can be used to learn the reduced order modeling, and we can use variational and this machine learning structure to discover these corresponding reduced order potentials. And the third example is diffusion models. So here we have two diffusion problems. One is the linear diffusion, one is nonlinear diffusions. So the free energy and dissipation potential are given by these equations. So all these two diffusion models can be described by these governing equations as we given before. And this is just the training data for the evolution of the concentration and flux. And here I want to emphasize is that for diffusion problem, if we don't assume boundary condition, if without knowing the boundary condition, such as knowing the chemical potential on the boundary, the free energy and dissipation potential are actually not unique. So for same evolution process, we can have multiple choice of free energy and dissipation potential. So here, I introduce an auxiliary function called psi hat. And with this function, we can reduce this equation to here, which actually tell us this is the constitutive law, and this psi hat itself is unique. But even though F and psi are not unique, we still use our Huang's architecture to learn both these non-unique functions. But finally, for comparison, we only compare the psi hat because it characterizes the constitutive law. So here is the learning results. This is for the linear diffusion and nonlinear diffusion. This is without extrapolation. The right-hand side is with a little bit of extrapolation. So the result is still very good. And even though the free energy and dissipation potential themselves are not unique, but the recovered the constitutive law to describe the diffusion is unique. So in summary, we propose a thermodynamic consistent neural net architecture to learn the non-equilibrium PDE based on Onsager variational principles. So we don't need to presume PDE, we only need the knowledge of the state and process variables. And we learn the PDE from the variational principle. And it has a strong statistical mechanics foundation, and it can be applied to a very wide range of problems, like the 3 examples I showed before. So this paper was published in JMPS last year. Okay, so then for the second project is predicting the unobserved statistical mechanics framework for non-equilibrium material response with quantified uncertainty. So first, I want to ask several questions. Can far from equilibrium material response under arbitrary loading be inferred from the equilibrium data and vice versa? Can we learn use the non-equilibrium response from one material and try to predict the response for different materials? And for this prediction, can we do uncertainty quantification for them? The answer is yes for all of them, as long as the system can be written by the stochastic differential equation. So here, the system we're interested in is written by the overdamped Langevin dynamics. So here, the target equation, target system, we call it S, is described by the potential V of the system. So here, lambda is the external protocol, or to be more simpler, it's just displacement boundary condition. And this psi is the Gaussian noise, the white noise. So since this is a stochastic process, it has infinite many possible paths during the evolution. So for each path, it has a probability, and that path probability can be given by this path integral formalism. It is an exponential of this path integral along the trajectory. So here we consider a different system, a simulated system, S tilde, with a different potential V tilde and a different boundary condition, lambda tilde. And with this path integral formalism, we can also write down the path integral for each trajectory for the simulated system, and they're in the similar equations, but with different V tilde and different lambda tilde. So here I'm interested in predicting the some microscopic observable O in the ensemble average of the target system, but we only want to use the simulated system information, the S tilde. So to do so, here I will reweight the path probability to change the ensemble average from S tilde, from S to the ensemble average on S tilde. So this reweighting process will introduce an extra reweighting factor, and this factor is related to the V bias, which is the difference of the two the potentials for the two systems, and also the noise that we had during the simulation for the target system, for the simulated system as tilde. So which means we only need to do simulation on S tilde, and as long as we know just the potential difference of the two systems and record all the noise during the simulation, we will be able to recover to predict some observable for the target system that we never simulated. So this strategy is actually called hyperdynamics. It is first developed to accelerate the MD simulations where the system trapped in local energy barrier, and we can just smooth out the energy barrier so that the particle will jump through the barrier easily to accelerate the process. And at the beginning, they usually use this to calculate some transition rate between different states of the system. But the original hyperdynamics does not include the boundary condition, and it only used to calculate some variable to describe the whole system. But here we found out it can be used to describe the whole evolution trajectory, not just some particular variable. And we also extended to include the displacement boundary change for the system. And in a more generalized understanding way, in statistics language, this is actually the important sampling strategy, just to reweight the system's probability from one path integral probability to another path integral path probability. So this strategy has several advantages. It can greatly accelerate the dynamics if we choose proper potential, and it can easily parallels in time. And since we only do simulation once, and then we can do the prediction after that. And we can also use this to predict the families of potentials just using one simulation. But they also have some challenges. For example, if we want to predict this system with this green potential, we can either start from the orange potential or the blue one. But since the blue one has a further distance from the potential difference is larger. So the path probability, the reweighting factor P bias, it also has a path probability. It also has a probability distribution. That probability distribution will be more heavy-tailed, which means during the prediction, the probability is hard to capture, and our prediction will be more poor compared to starting from a system with nearer potential. So can we do uncertain quantification for that? Yes, in theory. So this is the equation we use to do this prediction. So if we just choose this O as 1, we can find out this reweighting factor should have an average of 1. However, in reality, we don't have infinite number of simulation. We only have finite number of simulation. So the average of this reweighting factor is never 1. We define it as n. Then we can use the difference between n and 1 as an indicator to show how far or how good we capture the probability of the target system. And this difference can be estimated by the standard error of this n. And based on this equation and using large number theorem, we can use the standard deviation of this reweighting factor P bias divided by the number of realization of the system to calculate this standard error. And so here the question is how to calculate the standard deviation of the reweighting factor. So a traditional way to do so is use linear uncertainty estimate to do the variance propagation. For example, if we have a function f of a and b, we use the linear expansion, and we can find out the variance of f is the linear combination of the variance of a, b, and the covariance between a and b. And for the reweighting factor, based on the statistical mechanics, we can write down what is the expression for that, and use this method. We can finally write the variance of that factor is a linear combination of the variance of each Gaussian noise or we had during the long run simulation. However, later I'll show you this prediction totally failed. So here we propose a different strategy, which is a nonlinear uncertainty estimate. We will directly use the definition of the variance to calculate the variance of the p-bias factor. However, since the system is very difficult and like for arbitrary potential, it is impossible to do this ensemble average or the integral. So here we do a quadratic approximation to expand the potential to a quadratic series. And with this quadratic expansion, these two ensemble average will become two Gaussian integrals. And finally, we can write down the analytic results for the Gaussian integrals with some vector and matrix and this scalar, the ABC, or they are all related to the potential difference between the simulated and target system. And here is a result for a simple case. As we can see, the data itself is a green line that captured the variance of the p-bias. The linear uncertainty estimate totally failed, but our nonlinear estimates have captured the result very good. So here I will use two examples to illustrate our strategy. First one is a mass spring chain, which can be viewed as prototype for nanorods and some proteins or DNAs. So we'll start the system from Brownian motion, which means there's no interaction and no boundary condition. But we want to predict the system with quartic potential and a constant pooling velocity. So here is the results. The green line shows the results from Brownian motion. That's the ensemble average of Brownian. Everything is 0. So this is the displacement field, the external force, and the total work done on the system. And starting from the noisy Brownian motion, we can predict the orange line, and the true results should be the blue line. As we can see, when time is small, the prediction is very good. But when time becomes larger, the prediction will start to deviate from the results. So then we come to the uncertainty quantification to calculate the standard deviation of the reweighting factor, and then calculate the difference between the n and 1 to show how bad the prediction is. So when this difference reach like 0.1, which means 10% error, and this time is around 6. And for around 6, that's exactly where the results start to deviate from the true results. So this means our uncertainty quantification can show us when can we trust our prediction and when can we cannot trust the prediction. Second example is a 2D Glassy system with caging effect. So caging effect means for some 2D system, if the temperature is high, the system will behave like Brownian motion, but with some potential. But when the system is cooled down or the potential becomes higher, some particle will be trapped by its neighbor and will be very hard to go through its neighbor. So it will feel like trapped in a cage. So that's why it's called caging. Here we use two different system, one with a Hertzian potential, one is with Lennard-Jones potential, and with periodic boundary condition. We'll start predicting start to do simulation one system as tilde, and we try to predict the different system with the same kind of potential, but with a different potential amplitude. And with that strategy, we can actually predict multiple kinds of target system with different amplitude. I'll just skip the detail to save time. So here's the results. This is the Hertzian case. This is Lennard-Jones case. We start to simulate the process with starting from this dashed line. In this dashed line, in the log-log plot of the mean square displacement, it has around slope 1, which means the system is in liquid phase. It has Brownian motion. And we'll start to use this data to predict the system with different targeted higher potentials. And from up to down, the potential will become higher and higher. And the prediction are shown here. And as we can see, with closer potential, the prediction is good, but with higher potential, the prediction will fail when the time becomes earlier. But before the prediction failed, everything still looks very good. And we can see the slope decay becomes smaller than 1 and sometimes even reach a plateau, which means we already reached the caging effect. So which means we start from liquid phase, but we can predict the caging phase or the glassy phase. So furthermore, we do uncertainty quantification of this process. So here is some result for Hertzian and Lagrange potential with different potential difference. So first, I want to emphasize our UQ is only an estimate based on a quadratic expansion, but both Hertzian and Lagrange, they are not quadratic and they are actually far away from quadratics. So at the beginning, I didn't really expect our UQ to work. But from the results, we can see the prediction actually has a similar trend as the true results, and they're usually within the same order of magnitude. For example, here they're very similar, and this one is, although they have like half magnitude difference, but they have the same trend, so which is very good. And I also want to emphasize the plateau here and the decay. It implies the data itself is no longer accurate because we don't have enough realization. So it does not mean the UQ failed, it means the data failed. And finally, what I want to emphasize, this UQ is very fast. For each line, we only used 1 minute to calculate this line. And we don't even need to do the simulation for the target system, which means we do UQ first, and we can see how many realization we need to do to fulfill a good prediction until a certain time. And then we can start to do simulation for the target system, also for the simulated system. And finally, we do the prediction for the system we want. So in summary, we have a statistical mechanics approach to extrapolate material behavior. And this is used the hyperdynamics, and which is actually used important sampling as the essence. And we also provide a UQ method to do to estimate the uncertainty for this prediction, which has never done before. And finally, the strategy can be applied to very distinct systems. One is the elastic system, one is a diffusive system, and it also provides a strategy for material design in future study. And this work is also published last year in JMPS. And that's all. I want to thanks to my advisor, Celia, and all my groupmates, my committee, and my collaborators, and also to the funding resources. And thank you all. And anyone has questions.
Yeah, thank you, Shenglin, for your presentation.
Thank you.
I see a comment from the chat. Yeah, Shenglin, can you see the comment in the chat? So yeah. I think our audience asked a few questions there. Yeah, one question.
Mm-hmm. You benchmark your proposed architecture with simpler architecture, whether a difference. Okay. So I think the main part, the key part is first, for our method, we don't need to presume the PDE structure, or we don't even need to presume what kind of operators that they like. For some techniques like Cindy, they assume a library of the operator for the PDEs. So for us, we only need to know what is the state and process variable that we can obtain. That is, we can measure from the experiment or from MD simulations. And with that, we just use variational principle itself to discover PDE and then to recover the free energy and dissipation potentials. So this is first point. The second point is, more importantly, is before this paper, I didn't find any paper that's mentioned dissipation potential. I think this is still a not well-known concept, but it is a very powerful concept. So people usually know potential exists for reversible problem, but potential also exists for irreversible problem. So we can use dissipation potential to capture the irreversible dynamics for the system. So our paper is the first paper to encode both irreversible and irreversible part to recover the full non-equilibrium system evolution. Yes.
Thanks, Shenglin. Just to clarify the question. So if you were to solve this from a data-driven perspective, use a recurrent neural network like people have done for learning plasticity directly, like we've shown a few years ago.
Yes.
So you go data-driven, you're not trying to learn the operators or anything like that. Can you quantify the performance improvements? Are you using less data? Is your accuracy better?
Oh, actually, that's a good question, but I didn't compare with that. Yes. I'm not sure which one is better, but for us, I think the key point for us is this is a very generalized framework that can be applied to a multiple system, not just particular to a one class of system, but a wide range of problems. So maybe for a particular problem, I'm not sure will some system have a better performance, but I don't know. We can try to target on some like this viscoelastic problem or plasticity problem in the future. Yes.
All right. Thank you.
Thank you.
Hi. Hello.
Yeah. Hi.
Hi. Hello. So I'm Kerkus Hernandez from the University of Zaragoza, and currently I'm an intern at Brown. So my question is also related to variational Onsager nets. So once you have identified both potentials, the conservative and dissipative potentials, have you tried to perform the actual integration? So starting from initial conditions and integrating time?
Okay, yeah, that's a good question. To be honest, in this problem, no, because all three models are still toy problems with analytic solutions. So we only compare with analytic solutions. And at that time, I think it is good enough because they are the same. So we expect the prediction should be the same. But in reality, if we have some system without an analytic solution, we definitely need to see the evolution. And we're actually working on some more complicated problem now.
Okay, perfect. Thank you for the presentation.
Yeah, thank you.
Yeah, do we have any other questions, comments from the audience? George, do you want to add some comments? No?
No, it's fine. It's clear. Yeah, thank you. I asked my question. Yeah. Maybe you can inform everyone that there will be no second talk today, because of and Zogren. I don't know if everybody had, because there are like 51 people waiting for second talk, and there will be no talk. Can you please repeat why we don't have a second talk?
Right. Yeah. I was like, first speaker was supposed to be to give a first talk before Shenglin, but there's something wrong with the materials and the PowerPoint presentations. So for this week, we only have one talk, and so it ends at 1 p.m. And so if you have any questions for Shenglin, only one speaker today, so please ask, or we can close it. No? All right. Yeah, thank you, Shenglin, for your presentation, and thank you for agreeing to speak first on such short notice.
Yeah, thank you.
Okay, so this is it for this week's Chrome seminar. Everyone have good Friday afternoon and good weekend. See you next week. Bye.
Thank you, Shenglin.
Thank
Thank
you,
you.
Professor Kanyadakis. Yeah.